is accounting.
Okay, thank you very much for the chance of speaking here today. And so what I'm going to talk about is work with my collaborator Hiroshi Ritani on mirror transformations and the relation with potential functions that were introduced by Fukaya, Ota, and Ono. And the interplay between these two transformations, well, the function and the transformation will be given by a construction of Paul Seidel, and more or less in these 25 minutes I will try to explain that. So I first will introduce some notation about it. So for me, X will be a toric variety given by a fan, and I will assume that the one cones are generated by the elements B1 to Bm, and then so with this, you can define two sequences dual to each other. So the fan sequence, which is just taking the standard generators into the B i's that you choose, and then you take the kernel that defines certain lattice, and then you dualize this, and then you will get divisor sequence for that. And then you can think of these di's as the weights of the action on the big space CM. And then the L will be, as I was saying, the lattice of the torus that is acting there. And I will make these identifications along the way. So the second cohomology of X with integral coefficients will be the L dual. And then this will be the cohomology, the second cohomology, and so on. So the DIs, in this case, I will also think of them as being the Poincare duals of the divisors. Just, you look at ZI equals 0, those define divisors there, and then you take the Poincare duals of that. So for this talk, the phi's will denote the moment map, okay, for the action of GR. So the G will be the, well, for the people that knows, the torus that I am using for taking the quotient, okay, and then the T will be the torus that is acting on the toric variety. Okay, so those are just standard notations. So you take a maximal compact of the maximal compact of T, and then that's going to be just a product of S1s that acts on X again in a Hamiltonian way, and I will denote by this capital phi omega the moment map of that. The xi's in here are the homogeneous coordinates in X. And then, so the image of this moment map will define a moment polytope of it. And then if you take an inverse image of that moment polytope, then you will get a Lagrangian, okay? And then that will be a Lagrangian toric fiber that I will be dealing with. So I will use the term beta I as the classes represented by disks, for which the intersection with the divisors that you have will be just given by a delta function. So meaning they are represented by maps of this form with C1 to Cm. That the C1s will lie in the Lagrangian, and then the coordinate set at the ith coordinate, so that it intersects exactly once this divisor. And so it just happens that the Maslov index of this disk, the Maslov number of these disks, is exactly equal to 2. So the potential functions that I am referring to are introduced to Fukaya or Ota-Ono, as I said. So you look in this setting, you look at a manifold, a symplectic manifold with a circle action, and then you look at a Lagrangian, which is one invariant, and then you look at the moduli space of all genus 0 boarded disks, okay, with the boundary mapping into the Lagrangian, and then you look at a class in the second homology of the relative class with Maslov index equals 2, and then if you take the push forward of this moduli through the evaluation of the one marking that you have, then just by dimensionality counts, it just happens to give you a certain number. Okay, some people refer to this as the instanton number. I don't know really lots of physics, so times the fundamental class of L, and then you construct this function, which is a formal function at the moment. I will be more precise later on, which is just a sum over certain variables z to the b, the betas to the betas that I have, which are these classes, and then multiplied by the numbers n beta. So in the third case, I can be more precise, and I will like to explain what I mean by that, and also to introduce further notation. So to be more concrete, you take my sequence, the divisor sequence that I have above, you tensor it with let's see, star, and then you will obtain this new sequence. So I will call that a tori sequence. Then you look at the moduli space of complexified Keller classes, which will be a subset of this tori in there. And then I will look at the inverse image of that set, but in some sense bounded by requiring that all the norms of these to be smaller than 1. I will call that the open-close moduli space. And then every point in this open-close moduli space will be parameterizing certain triples. The triples that it parameterizes are Q's, L's, and H's, where the Q's are just the image of the map. Let me go back. So this is this map that appears in here. Okay. So I will denote that by Q, and then the omega gets determined. And then a Lagrangian fiber just by taking the logarithms of the norms of the zi's that I have, and then making negative. And then the H will be some sort of, well, in the case when the class beta, B that I have is 0, then there will be the holonomy around the boundary. But in general, it's just a lift of X IP. Okay, and so in this sense, with all this notation, the W that I have is can be interpreted as a function on the coordinates of this moduli. Okay, so this is the expression that appears in here. Okay, so with further identifications, so I already said that this sequence above was the fan sequence, and then you can identify this with the homology of the, for instance, the middle term with the homology of the pair, that one with the homology of X, and this one with the homology, the first homology of the Lagrangian. But further, you can actually just think of multiple classes, and then the EIs, which are just a standard basis in the lattice ZM, will map to the beta i's that I have, and those are the standard disks that I already defined before. And with this notation, I will introduce the Z to the beta, which are just elements in the group ring of this homology, and then for my beta, just as before, with these the generators. And then the Q to the D's will be the same coordinates but, that you are thinking of, just defined by the pairing of certain, the degree that I have. Okay, so the D is a degree in the second homology. And, but by choosing some generators, so an F basis of H2 of X, and then I'm going to fix that, and doing that identification, then I can essentially put the Q's in terms of the Z's in this standard way. So the QA will be denoting this product whenever I write the divisors as combination of the NEF bases that I have. So this is a tiny bit too technical at the moment, but so if you happen to assume that the toric variety is NEF, then you can actually go further and do a tiny bit more computation, and it happens to be that the potential function that I wrote above can be written in terms of the Z variables that I have here with certain correction terms that are explicit. And since I am only adding classes of Maslov index 2, and the beta i's that I have here have Maslov index 2, then the only contributions will come from degrees. So these are effective classes that intersect pair with 0. The pairing with the first-gen class is 0, and then you can actually have this computation in there. So if X is Fano, certainly those corrections do not appear, and then the potential would be just standard. So as an example, I think this is in the paper by Kenji and some other people. It's a pretty standard example, so you can think of the second Hirzebruch surface. And then this is the divisor diagram, and this is the fan diagram. So if you do certain identifications with the classes that you have, for instance, in my case, the P1 is denoting the fiber, and the P2 is denoting the section at infinity. So with that choice, the only contribution will come from the divisor that is actually not a vertex in the Fan polytope. So if you look at all these the BIs, and then you look at the convex hull of those, so the correction that appears come exactly from the divisor that from that corresponds to the B2. And so in general, I will use the notation, since I am inserting the Q variables in the Z variables, then I will use just this reduced notation R and K. In R is a K algebra in this case. All right, so what I want to explain is exactly how this has, where this mirror transformation of given tal comes into play. And so any questions so far? No? Well, certainly not for you. So the mirror transformation that, as we saw in the previous talk, is sometimes it appears as, you have two different models of the same thing, and then there is a change of coordinates. And in this case, this is what I want to explain. So Batyriev, whenever he suggested a formula for the quantum cohomology of a toric variety, he suggested that it was given by taking just this polynomial ring above there, so Q to W1 to Wm, then certain number of coefficients, and then divide by a quantization of the Stanley-Reisner ideal, and then just given by these relations, so imposing these relations. And actually, that's completely true if you assume that these classes are the divisors, and then if X is Fano. If X is not Fano, then it is now very well known that that's not longer true. You need to correct those generators, those divisor classes, and add something to that. So that was proven by Giventhal using his mirror transformation, and and also by Magdoff and Tolman using Seidel elements, and then therefore there is the connection that I want to clarify in a bit. Okay, so Seidel's construction goes as follows. So you look at, you take a circle acting on the symplectic manifold, and then you take two trivial bundles, disk bundles, on one side and another, and then you clutch them together using the action. That will give you an X bundle over P1, which is twisted by the action. In our case, since everything is toric, then this is the same as just taking the diagonal action in over C2 minus 0, and then the standard diagonal action, and then divide by it. And in that case, this is an identification. So what the idea is to count sections of this associated bundle of the action. So identifying all the fibers and then gluing all these sections together will give you an element in the quantum cohomology of X. In this case, I am using a reference section. So you just take a fixed section, and then you just bundle all these classes together. And then that will give you a element in quantum cohomology. Over here, I am. So this is a tiny bit horrible notation. I apologize. So you have to remove the Q that corresponds to the section classes, and then in that case, this will be an element in the quantum cohomology. And so the theorem of Seidel is that these elements are actually invertible, because if you take the opposite action, that will give you the inverse of this element. Okay, so it gives you some sort of an invertible element in the quantum cohomology. Okay, for the toric varieties that we have, there are m different in our case, right? So we have m different actions that we can take, and so we have m elements that perhaps we can use in order to explore the quantum cohomology. And whoops, oh, there you are. So okay, that's for that. There you are. So the Giventhal formalism goes as follows. So Giventhal's idea was to relate two functions, one which is entirely combinatorial, called the I function, that satisfies certain Picard-Fuchs equation, and then the J function, which is the Gromov-Witten function. This function over here, well, it has a pretty difficult explanation. Let me just say it very quickly. The phi i's that I have here, so those are bases of the quantum, the cohomology of X, and this is the dual basis. Psi corresponds to these insertions that you have, the universal Cottaneo bundle on the moduli space of genus 0 and 1 marking. And this is just a very combinatorial function. The two of them are cohomology valued. The DIs are the divisor classes. So you just take the product. And this is the product of the divisor with the degree class that appears in there. Okay, so if you note, there are two different variables, the q's and the y's, and the z's in the two cases are just formal parameters. So the idea of give and tell was that we know what type of differential operators actually kill this I function. And so if there is a way of relating this function and that function, then we know which differential operators will kill the j function as well. So given a differential operator that kills the j function will, in its own right, give you relations in the quantum cohomology, and that's the idea of give and tell. So since we know the I, then the j will give you the quantum relations, and that's exactly what his theorem says. His theorem says that if x is nef, and only nef in this case, then there is a change of coordinates, just given by the gi's that appear in here, in such a way that the I function and the j function are equal, and moreover, the ji's are entirely recovered by an asymptotic expansion of the I function. So that actually appears as a coefficient in here, and then you can read entirely the mirror transformation in this way. Okay, so as a corollary from his work, it's actually very, very simple to see that the quantum cohomology of the toric variety for an F toric variety is entirely given by just the battery of ring by using a change of coordinates as you have. Certainly the coordinates are a tiny bit more complicated, and then that's it. So the theorem that I proved with Hiroshi it goes as follows. So the mirror transformation that appears in here can be written entirely in terms of certain battery of elements. I will tell you what those are in a second. And this battery of elements are actually related to the Seidel construction in a direct way. So to tell you what this is, if you write the divisor classes in terms of the nef basis using the MIs as you have, then you just define this battery of elements as the same, but by using the Jacobian of the mirror transformation in there. So it's the same expression that you had before. And so the remark is that these actually do satisfy the battery of relations and also the additive relations that you will expect with the divisors that you have in here. So they are the same. The Seidel elements do not satisfy those linear relations. And so that's essentially the discrepancy that appears in there. And so the theorem that we have is that actually you can give an explicit relation between the Seidel element and the battery of element in terms of certain hypergeometric function, which is entirely explicit. Actually, as a matter of fact, this term that appears in here is a mirror symmetry coefficient that corresponds to the section class if you apply the mirror theorem but to the E bundle, to the associated bundle in the Seidel construction. And so we have an explicit expression for that. And again, this formula is entirely combinatorial. So you can just look at the expression in the expansion of the I function and then learn about it. So it's very explicit. And then the contributions for this come exactly as from the non-vertex divisors, meaning in the fan. If you look at the fan, the convex hull of the vectors BI that I had at the beginning, the ones that do not correspond to vertices, those are the ones that will be giving you contributions for that. And so several people noted, and at that time, that there is no other thing that can happen, but that the correction terms that appeared in the potential suggested by Fukaya et al. Have to be the same as the correction terms that we have, and these are explicit. This is an explicit computation. And so, so let me just give you a quick example. Well, I mean, perhaps I don't have time. So, yeah. I don't know, like probably 7 minutes. Okay. Okay, so we're fine. So quickly with the computation. So I am using F2, so you can actually just do it by hand, the same thing that we have. So the proof of the relation that I did is applying the Giventhal mirror theorem to the associated bundle. And so in that case, the only thing that I haven't mentioned is that if X is Neff and I am using the actions that will fix the devices, then this associated bundle will be also Neff. So it's not going to be over-twisted. And so you can just apply the mirror transformation of Giventhal and then get the relations that you have. So in this case, the Seidel element and the Seidel and the battery of element are related exactly by that correction term that appears in here. So this is the proposition that I just said, that the correction terms do not appear if the BI is not in the vertex. Okay, so now for the idea of the proof, I'm going to assume some conjecture. Unfortunately, I am not yet done with the proof of this conjecture. We are not done with the proof of this conjecture. So the idea is that you can do the same construction of Seidel in the case where you have a Lagrangian boundary, in this case a toric boundary. So you look at the moduli space of sections of this bundle, okay, over the disk, and you impose that the boundary of this section actually lies in this space. So it's the Lagrangian times S1. So this is the trivial bundle in there, and then they generate the target to so that you get the Seidel construction on one side and then a trivial bundle on the other side. This side that appears in here is because if you are twisting by the action here, then the other one has to be twisted by the opposite action. But ignore that part. Now the moduli spaces that are involved is this moduli space. This is a Seidel element with one marking, but it's targeting into the divisor X. And then this is a relative version of the space of disks, where you have an internal disk and an internal marking, and then one marking at the boundary that will map into the Lagrangian. And then, so if this formula is correct, which we believe it is, then and using this degeneration argument, then what we can prove is the following. So this is the implication. So just as we bundle all the sections into this invertible element, the Seidel element, then we can do the same in this construction to get an element in the cohomology of X, L. Okay, so just as the Seidel element was. And over here, you can think of this as an equivariant extension of the Seidel construction, because this cohomology, X, L, is essentially the equivariant cohomology of X. And so you can think of this as an equivariant lift of the Seidel element. So I'm going to use this notation where dx to the beta is the same as beta tensor z to the beta. So I am attaching coefficients, the exponents, the exponents of the z's as coefficients. And then I will define, so suppose that this happens, and then that whenever I pair this class, okay, this extension, with the derivative of one of the coordinates of the superpotential, then I will obtain delta. So this is just the standard delta jk zj. And so with that, we call this the Kodaira-Spencer map that goes from here to there that maps in the natural way. So you take all the divisor classes and then it maps into these derivatives. Then what happens is that the image of this element is exactly Zi, and then this map will descend to the cohomology, not the relative cohomology, but to cohomology, and then it will force to map into the class defined by the Zi. So this is essentially the claim of the generation formula that I have. And then with that, if you set the bj, this class to be just the Seidel element times the correction term, this is the correction term of the superpotential, then you will see that this class is actually going to map into the Wi, and then it forces certain linear relations on the classes of the Wi's that you have. So then I have, so far I have that it satisfies the linear relations, and then it's easy to prove. Actually, this is a theorem, perhaps, of other people that of CLLT, that these correction terms also vanish if the BI is not a vertex of defined polytope, and then in that case we have a theorem in one of our papers that those elements, if they satisfy all these conditions, then there is no other thing but to agree with the battery of element. Actually, we know that that characterizes entirely the battery of element. And then the FIs should be exactly the correction terms that I have on the devices, these correction terms. So I think I'll stop here.
So the main result is that the battery of elements are expressible in terms of the Seidel elements.
That's right.
That doesn't involve any Lagrangians.
That does not involve any Lagrangians.
Is there a proof that doesn't involve any Lagrangians?
Yeah. So we do have a proof of that statement. Now the problem with the Lagrangians is, you need this lift, to prove, to do what I just did, because these FIs actually are defined, using Lagrangians.
Yeah. So you're saying you can prove that the equality without using the Lagrangians, but if you also want to say that the open disk potential.
That's right. Appears from that formula, then I need to do the construction. Yeah. So that's pretty much there.
So you run the same argument in non-Fanon case, then you don't have enough.
I don't have enough information. Actually, that's a very good question. I've been toying with that for quite a while. And well, first off, Giventel's theorem does not apply, right? So there is a version of Giventel's theorem, but it's very cumbersome, and I don't think I can handle those computations at the moment. Hopefully soon.